Hey everyone, so we are done learning Java. We are mostly done learning about software engineering, except of course the actual experience of software engineering. Now we're going to move on to the data structures part of the course, and sort of a prelude to this is first we need to learn about asymptotic analysis, how we analyze the running time, the memory use, and other aspects of algorithms. So to motivate asymptotic analysis, imagine that you're writing an algorithm that processes a real retail store's inventory. So at the end of each day, you need to keep track of how many items were sold, how many items were brought into inventory from manufacturers, and so forth. And imagine that each day's inventory involves two tasks. First of all, it takes 10,000 milliseconds for your program just to read the inventory from disk. So you know how much you've got in your warehouse. And then it takes 10 milliseconds to process each transaction that happened today. And so if you have n transactions that happened in a day, then the total amount of time it takes to process all of those is going to be 10,000 plus 10 times the number of transactions, milliseconds. Now, 10,000 is a much bigger number than 10, but the number of transactions might be even bigger than that. The number of transactions that go on in a large company might be millions per day. So we get the sense that even though that 10,000 millisecond overhead is a lot, that ultimately, as our company grows bigger and bigger, that's not what we're going to have to worry about. We're going to be worrying about that 10n milliseconds per transaction. So this part of the term becomes more and more important as your company gets bigger, your number of transactions gets bigger, or if for some other reason n is very large. Now, we also know that these numbers, 10,000 and 10, are particular to the computer we're using today. Tomorrow we might buy a faster computer and those numbers will get smaller. We might have a better compiler, a faster operating system. All of this technology hopefully will improve. And so the numbers 10,000 and 10 are going to get smaller and smaller as technology improves. But there's still something essential here that's never going to change no matter how good or how fast the computers get, and that's that the amount of work we're going to do is still going to scale according to the number of transactions we need to do. And if you have twice as many transactions, it's going to take approximately twice as much time, regardless of the particular computer you're using. So what we want is a mathematical way to abstract that intuition and say the important thing going on here is that there is linear growth with the number of transactions. Computer science has a very formal mathematical way of doing that, and that is called big O notation. And you've seen a lot of this, but probably without the mathematical formalism. Big O notation is generally used to specify upper bounds on something. Generally, it's upper bounds on the growth of a function as n, the input size, approaches infinity. Most commonly, the thing that we're trying to bound is the running time of a program that we wrote, but not always. Sometimes we're trying to bound the amount of memory it uses or some other fact about the program. So, we're going to assume that there is some independent variable n, which is the size of the program's input. Exactly how we measure the size of the program's input doesn't usually matter. It might be the number of inventory items, it might be the number of words, it might be the number of bits. Usually when computer scientists are going fully formal, it's the number of bits. But for reasons we'll see, it usually doesn't matter, it's just a constant difference. What we really care about, though, is what is the behavior of a program that we wrote as n approaches infinity. Now, typically, there is a function, t of n, which is an empirical function that we really care about. Now, for example, t of n might be the running time in milliseconds. It doesn't have to be. It might be the memory use in bytes. But whatever t of n is, it's a real-world empirical function that you could actually measure. Exactly how many milliseconds does it take for my program to run with a particular input? And that's usually a pretty complicated function. We don't know it exactly, but usually we can still bound it in one important way. What we're going to do is we're going to look for another function called f of n that we think characterizes the important part of the running time or the memory use, but is much simpler. So we want f to be as simple a function as possible. Because you know the real running time as a function of the input side is going to be terribly complicated. So I'm going to say this informally first, and later I'll say it, give you a much more formal definition. We say that t of n is in big O of f of n if and only if t of n is less than or equal to some constant times f of n, and that has to be true whenever n is big enough. And that has to be true for some constant c. Doesn't matter what the constant is as long as a constant exists. So usually you can just pick some big constant c. So what I've just given you is not a rigorous definition. It's just intuitive hand-waving. And the obvious question is, when I say whenever n is big, how big do I mean? Well, usually I'm trying to prove that some complicated function t of n is in big O of some simple function f of n, and I'm allowed to scale f of n as much as I want to make t of n fit underneath c times f of n. So in other words, I can pick n as big as I want, and I can pick c as big as I want. And I'm going to deliberately try to pick them big enough to make t of n, if you draw it as a graph, fit underneath c times f of n. And likewise, how large is c? Well, same answer. The way big O formalism works is I get to pick this constant c, I get to pick how big n is, and I'm trying to prove that this inequality here is always true for the choices that I have made. Yeah?
So, but we have a strict restriction that as n goes to infinity and c cannot be infinity, c must be some finite number.
Yes, absolutely. C has to be a finite number that doesn't change as n increases. So to give an example of this, hopefully to try to clarify this a little, let's come back to our inventory. And let's consider that function that we've already looked at for the inventory program, which is 10,000 plus 10 times n, where n is the number of input items, the number of inventory records. And that's how many milliseconds our program takes to run. What I want to do is I want to prove that this is in big O of something simple, so I'm going to try out something simple. In fact, I'm going to try out the function n, because I can't think of a function of n much simpler than n. Maybe 0 is a simpler function, but that's not going to work. So what I want to do is I want to show that there's some constant for which I can prove that that inequality I showed you always holds, at least when n is big enough. So to make this work, turns out that if I pick c to be some reasonably big number, then it'll work, as long as c is big enough. So I'm going to pick c equal to 20, because it works for that. And now I want to draw a graph of what these functions are that I'm comparing. So n is the horizontal axis, and we're going to plot these functions of n. And the function that we care about, t of n, starts at 10,000 on the vertical axis and goes up from there. So that's the function that shows the actual running time of our program. And now I want to show that that complicated function is in big O of n. And so the way I try to do that is I pick this constant, c equals 20. I multiply 20 by n, and I graph that. So here's a graph of 20n. And where do those two lines intersect? It turns out they intersect when n is equal to 1,000. So that intersection point happens for n equal to 1,000. And so what this graph tells me is that for any value of n greater than or equal to 1,000, the inequality that I wanted to show is true. T of n is less than or equal to c times f of n, where c happens to be 20 in this case. Therefore, I can say that T of n is in big O of f of n. And saying that T of n is in big O of f of n is just a way of telling, well, just pardon me, saying that T of n is in big O of n saying that T of n is in big O of n is a way of telling a fellow computer scientist that the running time of this program scales linearly with the size of the input. That's not true of all programs. Some problems are harder to solve than others. Inventory is pretty easy, but there are a lot of problems in computer science where it takes a lot more than linear time to solve the problem. So what I want to do is, now that I've got this example, I want to wrap this up with now giving you the real rigorous definition of big O, which is something you should commit to memory. What I'm about to write is the central idea of today's lecture, and it will bear on your entire career as a computer scientist, no matter how abstruse it seems right now. Formally, here is the definition of big O. Given a function f of some variable n, big O of f of n is a set. It is a set of functions So it is the set of all functions that satisfy the following statement. There exist positive constants, C and capital N, such that for those two constants the following is true. For all values of little n bigger than that positive constant, the running time or the space use or whatever is less than or equal to some constant times f of n. So taking this definition and going back to the graph we had here, big N is this constant 1,000. So the idea here is I have graphed two different functions. I'm trying to prove that one of those functions is big O of the other function. And to do that, I need to stuff the one function underneath the other function so that it stays below the other function. But it doesn't have to be below for all values of n. It only has to be below for sufficiently big values of n, or in the limit as n goes to infinity. So I want to show that that line is always underneath this line if I scale it properly. But it's not that line is not underneath this line here, but when I go above 1,000, then it's always below that other line. So I'm allowed to take this vertical line and move it as far to the right as I want, just as long as there's some place I can put that vertical line so that everywhere to the right of that vertical line, the t of n function is underneath the scaled f of n function. Then I have proven what I want to prove. So are there questions about this? Yeah? Is it correct to say that O of n is? It's a subset. Yes, it is. So the question is it correct, given this definition here, to say that big O of n is a subset of, for instance, big O of n squared? And yes, that is absolutely true. And we'll see a little bit more of why later. But when the function gets to a larger growing function, then now you have a bigger set of functions with big O notation. Other questions? Yeah? So the question is, are there times you might be concerned only about what happens when n is between 0 and 1,000, and you don't really care about what happens as n goes to infinity? And there are a few places where you care about that, but there is not a standard mathematical notation for talking about those. So I want to give some examples, and these examples will also give you some idea about how big O notation is used and what it means and what it doesn't mean. So the first example is if I take a really, really big number, like 1,000,000 or 1,000,000,000 or 1,000,000,000,000, whatever, and multiply it by n, that is in big O of n. And proving that is really easy. You just choose the constant c to be really large. Like, say, 1,000,000. And then you can choose big N to be anything. Doesn't matter what. So the important thing to understand here is that big O notation does not care about constant factors. Or it doesn't care about most constant factors. It doesn't care about a constant factor by which you are multiplying your entire function. If your running time is 1,000,000 times slower, big O notation doesn't tell you that your running time is 1,000,000 times slower. It just tells you that your running time is linear in the size of the input. So, computers in the 1950s were at least 1,000,000 times slower than computers today, but algorithms for doing inventory ran in linear time in 1950 and still do today. So another way to say this is you can write big O of 2 of n. That is exactly the same set as big O of n. That is exactly the same set as big O of 1,000,000 n. The constant doesn't matter. And so it's unnecessary to write the long version. Computer scientists usually just write big O of n because throwing an extra number in there is just redundant. It doesn't make any difference. So we usually use the simplest version of any big O expression. And big O of n is simpler to write and contains exactly the same information as big O of 2n or big O of 1,000,000 n. So it's unnecessary but not wrong to write big O of 2n. Just extra ink for no reason. Another thing worth understanding, related to the question a few minutes ago, is it is a fact that n is in big O of n cubed, for instance. So n cubed is an inherently much faster growing function than n, but big O only gives you an upper bound. It doesn't give you a lower bound. So is n cubed bigger than n? Well, as n goes to infinity, it sure is. So this is a true expression. You can prove this by just choosing the constant multiplier 1. And it is a fact that n is less than or equal to n cubed for any n greater than 1. So big N is 1. So it's important to understand when you're reading big O expressions that they only give upper bounds. And just because an algorithm's running time is in big O of n cubed doesn't mean it's slow. Because an algorithm whose running time is in big O of n cubed might also be in big O of n, in which case it's fast. We're going to learn a different notation on Wednesday for saying that an algorithm really is slow. But big O notation is not that notation. Big O is an upper bound only. And let me draw this example just to clarify, just to give another example. Here's n on the horizontal axis. Here is the function n. And here is the function n cubed, which starts a little slow but then grows really, really, really fast. And the two cross over each other at big N equals 1. And then as you go further to the right, n cubed grows really, really rapidly compared to n. A third example that shows us another aspect of big O notation is let's add a bunch of different functions together that each grow at different rates. So n cubed plus n squared plus n. Well, the fastest growing of those three things is n cubed. N cubed is going to grow so fast that as n goes to infinity, the n squared plus n portion isn't even going to matter. And big O notation expresses that fact by the fact that this is in big O of n cubed. It is not in big O of n, it is not in big O of n squared, but it is in big O of n cubed, meaning that n cubed is the dominant term. N cubed is the fastest growing term, so we say it's asymptotically dominant. And the way you would prove this, well, one way is I'm going to set the constant c equal to 3, because that way 3n cubed is going to be greater than n cubed plus n squared plus n for any n larger than 1. And so again, the principle here is that big O notation is usually used only to indicate the dominant or biggest or fastest growing term. When n is really big, the other two terms stop mattering. The n squared and the n just fade out to being negligible compared to that huge n cubed term. Any questions about any of these examples? Question there?
Yeah, so for number 2, why can't say it's like 5 times n squared with n cubed?
Sorry, what's the question?
Like you said, n is like a subset of all n cubed.
Mm-hmm.
Why can't it be a subset of n squared?
Can it be a subset of n squared? It certainly can. So I gave an example here to say that n is in big O of n cubed, but it's also correct to say that n is in big O of n squared, and it's also correct to say that n is in big O of n to the fourth. Is that answer your question, or is there more to it? Usually you would not write this because it's kind of misleading, but I'm just pointing out a fact about how big O notation works. If someone says that an algorithm runs in big O of n cubed time, it could mean that they have a proof that is no slower than n cubed, but they don't know it might be even faster than that. When you get into algorithms research, actually there's a lot of circumstances where you have algorithms where we don't know exactly how fast they run. And so we might be able to prove that this algorithm runs in big O of n cubed time. We suspect it runs in big O of n squared log n time, but we don't know for sure. And so often we use big O just as an upper bound because we don't actually know the true running time or the tightest possible provable bound on the true running time. So sometimes we give a bound that's a little bit slack because that's the best we can prove. Yes?
Big O notation doesn't care about most constant factors, but it cases where it does. Or it doesn't.
Or what does?
You said that big O, for number 1, for example, when you said big O notation doesn't care about most constant factors.
Right.
So is there a case where it does?
Yes, and I'll talk about this in more detail right now, but just as an example, if you have, we know that 2 of n is in big O of n, but if you take an exponent of e to the 2n, is that in big O of e to the n? Well, absolutely not. That is not true at all. The e to the 2n grows much, much faster than e to the n. So it matters where the constant is. If the constant is just in front of the function, then it makes no difference. If the constant is buried somewhere inside the function, then it might make a big difference. Other questions? So to help you figure out which terms dominate which other terms, here is a chart of the terms that tend to come up most often in algorithms research and algorithm analysis. And I'm going to give you a list of these big O sets in order from smallest to largest, or slowest growing to fastest growing, or happiest to saddest, to put it another way. So usually the slowest growing function that we deal with on a regular basis in algorithms is big O of 1, which means that as the input size grows, some parts of your program don't get slower at all. So we call this constant time if the running time has nothing to do with how big the input is. That is a subset of big O of log n. And you might recall that we have seen a log n algorithm called binary search. You have an array of length n. It's already in sorted order. You want to find a particular item. If it's in the array, that takes log n time. And formally, mathematicians say that takes logarithmic time. But it's quite common in algorithms for powers of the logarithm function to come up as well. So you'll see log squared and even log cubed in a lot of algorithm analyses. But logarithms grow more slowly than square roots. And square roots of n, of course, grows more slowly than n itself. And any program that runs in big O of n time is said to run in linear time. There are a lot of algorithms that run in n log n time, and that includes the most popular sorting algorithms. So you want to sort the phone book, usually people will use an n log n algorithm. And this one actually doesn't really have a name, people just call it n log n. And that is faster than something that runs in n squared time, aka quadratic time, which is faster than something that runs in cubic time, or n cubed time, which is faster than something that runs in quartic time, which is what we call n to the fourth. And n to the fifth is called quintic, but I'm not going to go that far because at that point we don't get very many algorithms that go there. So next I'm going to jump to algorithms that run in exponential time. And I should mention that there are many different kinds of exponential time that are not asymptotically equal to each other, but asymptotically dominate each other. And they're all called exponential, but that doesn't mean they're all equally fast growing, because some functions are more exponential than others. Yes?
Two questions quickly. First off, so if log squared is considered to be slower than square root n, is log to the any power faster? Is log to the any power faster than square root n?
As a matter of fact, yes. So a log to the 100th power, you can prove that as n goes to infinity, that grows more slowly than the square root of n. Or log to the millionth power still grows more slowly than square root of n. In fact, log to the millionth power grows more slowly than big O to the of n to the 1.00001, for instance. I'm sorry, to the 0001. Let's make this really astounding. So yes, anytime you're growing by a power of n, in the limit as n goes to infinity, that's ultimately going to be bigger than any logarithm to any constant power.
Okay. Also, why is n log n so common? That's an extraordinarily common runtime for many algorithms. Why is it so much?
N log n is common because there are so many algorithms that sort of do divide and conquer in a linear time style. So you get n elements, and you have some linear time operation that divides and conquers them by breaking them up into two equal groups, and then repeats the process of breaking those up into two different groups, and so on all the way down until you get down to individual items. And so what happens is that you wind up with a computation tree in which you have log n levels of computation, and at each level of computation you have to do n work. And we're going to see we're going to see a few algorithms this semester that do that, with merge sort being the most obvious one that follows exactly this structure. Other questions? Louder, please. I didn't hear. What is the C? You mean, what are the constants you would use to prove each of these? Okay. All right, so algorithms that run in n log n time or faster are pretty much always, in almost all circumstances, considered efficient. And algorithms that take n to the 7th time or more are usually considered useless, with some exceptions for very small problems. But there's a big gap between those two where an algorithm may or may not be considered efficient. Does an algorithm that runs in n-cubed time efficient? Most matrix multiplication algorithms, for instance, run in n-cubed time. There are ways to make it faster if n is really large, but when you're going to deal with matrices, pretty much you're in the range of somewhere between n to the 2.5 and n to the 3, which is cool. If you have, say, 10,000 by 10,000 matrices, you can do that. If you have billion by billion matrices, you can't do that. So what is and what is not efficient really depends on what kind of problem you're trying to solve and how big the data is. And by the way, I just want to remind you again, if there's anyone in the room who's still not comfortable with logarithms, you really, really, really need to understand logarithms for what's coming in this course for algorithm analysis. So again, if you don't feel totally comfortable with them, grab your Goodrich and Thomasia textbook and reread sections 4.12 and 4.17. Because computer scientists really do need to know logarithms in their bones. Any more questions? I'm sorry, can you talk a little louder, please? M to the power of log n. Let me write that down. What about it? What's the question? Where would it fit? Let me think about this a second. This would be something. One way to write this is, let's see, and log n. Is there a good way to simplify this? Mm-hmm. Well, it's definitely bigger than any n to a constant, but it is smaller than any traditional exponential function. So I am pretty sure it would go in here. There's probably some way to simplify it, but I would have to think about it longer than I have right now. So I would put it between n to the some constant and some constant to the n. Question over here. O of n factorial. Is less than or equal to than n to the n, but it's greater than or equal to than 2 to the n. So it's well up in the exponential range. It is hard to isolate exactly where it goes between here and here, but that gives you a rough idea of where it lies. You guys have a taste for weird functions. I like that. All right, I want to give you some warnings now about the abuses of big O notation or mistakes you might make if you don't fully understand what's going on. So let me start by giving you a fallacious proof, and please tell me what is wrong with this proof. I'm going to claim that n squared is in big O of n, and the way I'm going to prove it is I'm going to choose c equal to n, and by choosing that, then now the statement that we want to prove is that n squared is always less than or equal to some constant times n. So if I choose the constant equal to n, then my statement is n squared is less than or equal to n squared, which obviously is always true. So therefore, n squared is in big O of n. N's not a constant, thank you. So when I say that c must be a constant, what the word constant means is that it cannot depend on n. So I cannot set c equal to n. That defies the meaning of c being a constant. All right, a second thing I want to get across is that big O notation just expresses a mathematical relationship between two functions. It does not say what those two functions are. You have to specify that separately. In particular, it does not always mean the running time of your program, or the worst case running time of your program. It might mean that, sometimes it does, but it doesn't have to. So when you just use big O notation, that by itself does not say what the functions mean. In addition to the big O notation, you have to have extra words that say what those functions are. And the function on the left is not necessarily the worst case running time. For instance, the number of emails you send to your mom as a function of time might be the time, big O of time squared, in which case not only are you a very good child, you're an increasingly good child. To give you some more examples, in binary search on an array, We can talk about the worst case running time using big O notation. That happens to be in big O of log n when you're doing binary search on an n-element array. But I can talk about lots of other properties of binary search as well. I can talk about the best case running time. What does that mean? Well, the very best case for binary search, the very fastest it can run, is when the thing you are looking for, you find it right away. The very first element you look at in the middle of the array, that's the one you're looking for, then you can return that element and stop immediately. Therefore, the best case running time is in big O of 1, because sometimes you get lucky and you just find what you're looking for right away and you're done. We can also talk about the memory use of binary search. Well, when we talk about memory use, we usually include the input. And in a binary search algorithm, most of the memory that we use is the input array. And we use maybe log n in memory on top of that, but the input array takes linear space. And we could talk about things that are just sort of random functions. It is perfectly correct for me to say that 47 plus 18 log n minus 3 over n is in big O of the worst case running time. So what I want to get across is that every semester there are a few students who, when the midterm comes around, they get it in their head that big O of n means the worst case running time is in big O of n. Big O of n by itself is just big O of n. It's a set of functions. It does not say worst case running time. You actually have to read whatever's written and see what this big O applies to, which may or may not be the worst case running time. So don't let your brain short out if the question uses big O in some other way, like memory. A third thing I want to talk about is, well, I'm going to come back to the exponentials again, the exponential example. I told you that constant factors usually don't matter, and then someone asked, so I gave an example showing that they don't. I want to come back to that again. Let's suppose that somebody incorrectly says that e to the power of 3n is in big O of e to the n. Because constant factors don't matter. Or a similar example is when the constant that we're taking an exponent of changes. So you might think 10 to the n is in big O of 2 to the n because constant factors don't matter. Well, if you're just multiplying the whole function by one constant, then the constant doesn't matter. But that's not what's going on here. So these constant factors do matter. Specifically, these claims are wrong because, well, e to the 3n is bigger than e to the n by not a constant factor, but by a factor of e to the 2n. If you divide e to the 3n by e to the n, the factor separating them is e to the 2n, and e to the 2n is a really fast-growing function. It's not a constant at all. Likewise, 10 to the n is bigger than 2 to the n by a factor of 5 to the n. So that's another really fast-growing function. So don't make that mistake. And the last thing I want to point out is that big O is usually a good way to figure out that one algorithm is faster than another. If one algorithm runs in n log n time and another one runs in linear time, the linear time algorithm is usually faster. But there are exceptions to that rule if the constants are way out of whack. So for instance, suppose that you have one algorithm whose running time is n log n exactly in seconds. And here I'm specifying the base of the logarithm just because this is supposed to be an exact running time in seconds. And suppose there's another algorithm that runs in time 100n. Well, the first one is asymptotically bigger. It's bigger as n goes to infinity. T of n dominates u of n asymptotically. So if you are actually have n going to infinity, you should use the second algorithm, u of n. But in the real world, n is not likely to be much bigger than 2 to the 30. Well, maybe 2 to the 50. Inputs only get so big. You're not going to have something that has an input size of 2 to the 100. So the fact is that although asymptotically un looks faster than tn, because of that constant 100, it's only faster when your input size is larger than the number of subatomic particles in the universe. And that's not going to happen. The bottom line is that in practice, log of 2n is less than or equal to 50 in practice for any input size your computer will ever be able to handle in one human lifetime. And so log n usually means slow, but 50 means slower. The reason why we can usually count on just looking at asymptotic running times is because usually algorithms don't have these constant differences of 50 between one algorithm and the other. But when they do, you may be better off choosing the n log n algorithm over the constant time algorithm. On Wednesday, I will talk to you more about asymptotic analysis and algorithm analysis.